Thank you, Jacob. Hello, everyone. Thank you for attending the webinar. The title of the webinar for today is Evaluation of Managed Lane Facility in a Connected Vehicle Environment. So firstly, let's look at the research background. Previously, several studies have been conducted at the University of Central Florida to evaluate the safety and operation effectiveness of managed lanes. For example, the team investigates the optimal weaving distance in a freeway segment of I-95 in Miami, Florida, with 4 general-purpose lanes and 2 managed lanes. The results of optimal weaving lengths from the driving simulator experiment were found in consistency with the results from the microsimulation. It was recommended that 1,000 feet to be used as the optimal length for per lane change at the general-purpose lane weaving segments with managed lanes. In recent years, connected vehicles are one of the most recent developments in traffic and safety engineering. They have the potential to improve safety and efficiency by reducing the number of crashes and fatalities on the road. This technology enables vehicles, roads, traffic signals, and other infrastructure to communicate with one another about the current road conditions, alerts, and signals. Thus, one of the objectives of the research is to analyze the safety and operational effects of adding connected vehicles and connected vehicle lanes to the managed lanes network. So, in first section of the project, we built networks for various connected vehicle lane designs with different market penetration rates in the managed lane network. We also aim to determine the best connected vehicle lane configuration based on the safety and operational measures and found the optimal market penetration rate for each design. Last but not least, this study proposed recommendations to the transportation agencies for improving the safety and efficiency of connected vehicle lane design on freeway facilities with managed lanes. For this experiment, a 9-mile corridor located on I-95 in South Florida was used in this study. As shown in the figure, the corridor consists of 4 general-purpose lanes and 2 managed lanes, 7 on-ramps, and 9 off-ramps. The network of interest was built in Vism, which is a microscopic traffic simulation software with the same geometric and traffic characteristic as the field network. Traffic volume, traffic speed for each lane in the corridor were used to calibrate and validate the simulation network. In the first simulated network, the traffic data was inputted at a 15 minutes time interval. The peak period was defined from 7 a.m. to 9 a.m. and the off-peak period from 9 a.m. to 11 a.m. A 30-minute simulation was added at both the beginning and the end of the simulation for warm-up and cool-down. Multiple vehicle types were inputted into the simulation network, including passenger cars, carpools, and heavy goods vehicles. The percentages of the inputted vehicles were 85%, 10%, and 5% for passenger cars, carpools, and heavy goods vehicles respectively. The GH value was used for the calibration process. The GH value depends on the traffic volume in the field network and the traffic volume in the simulated network. A low value of the GH is preferred for the study. The average GH value and the percentage of GH value less than 5 indicate that the simulated network was well calibrated. Also, the differences between the field traffic speed and the simulated traffic speed was used in the validation process. Previous studies indicate that if the percentage of speed difference lower than 5 miles per hour is higher than 85%, the simulated network is considered well validated. In this study, the average speed difference and the percentage of speed differences lower than 5 miles per hour indicate the simulated network is well validated. In order to study the effects of connected vehicles and connected vehicle lanes, different cases were studied in this project. Firstly, the base condition includes the I-95 corridor with one access zone. Connected vehicles were not included in this case. In case 1, connected vehicles are only allowed in the managed lanes and have the choice to use any of the managed lanes. In case 2, the connected vehicles can use either the managed lanes or the dedicated connected vehicle lane. In case 3, connected vehicles are only allowed to use the dedicated connected vehicle lane. In case 4, one general-purpose lane was converted to managed lanes. Connected vehicles have the choice to choose any of the managed lanes. In case 5, connected vehicles had the choice to use any of the dedicated connected vehicle lane, managed lanes, or general-purpose lane. In total, 90 scenarios include the base case for peak and off-peak conditions were tested in the study, with different connected vehicle lane configurations in the managed lane network in both peak and off-peak conditions. Various market penetration rate was also considered in the scenario design. The table presents the 90 studied scenarios. For each scenario, 10 random runs with different random seeds were applied. In case 1, 2, and 3, the maximum studied market penetration rate was 40%, because when the market penetration rate is over 40%, the managed lanes have reached their capacity. In case 4, the configurations of the lane were changed in order to increase the capacity of the network. Hence, in case 4 and 5, the studied market penetration rate reached 100%. Similarly, in case 5, the studied market penetration rate reached 100% because connected vehicles were allowed to use any of the lane in the network. The SSAM was adopted to determine the potential conflict frequency, which is associated with the number of crashes in the field. Two types of conflicts were used in this study: rear-end and lane change conflicts. As provided by SSAM, the rear-end conflict was considered when the conflict angle was between 0 and 30 degrees, while the lane change conflicts were defined as when the conflict angle was between 30 to 80 degrees. The crossing conflict was excluded from this study since the percentage of crossing conflict was less than 1%, and crossing crashes are less likely to happen on freeways. Recommended market penetration rate percentage is shown in the table in these slides. Based on the result, a market penetration rate lower than 10% was not recommended in this study, since no significant reduction of conflict was observed. Also, case 3, which is when connected vehicles are only allowed to use the dedicated connected vehicle lane, was not recommended. It has no significant improvement compared with other conditions. The traffic operation measurements was also analyzed to assess the operational effect of adding connected vehicles and connected vehicle lanes on freeway facilities with managed lanes. The evaluation measures for the traffic operations include the average travel speed and average delay. The findings of this study have several implications for future practice and policy. First, the finding suggests that when the connected vehicles were only allowed in managed lanes, a market penetration rate between 10% and 30% was recommended. For these cases, a market penetration rate of 40% or more was not recommended. The case allowed second, the case allowing connected vehicles connected vehicles only in the connected vehicle lane was not recommended since it has no significant improvement than the base case with no connected vehicles. Third, when converting one general purpose lanes to managed lanes, the market penetration rate could be improved to reach up to 60%. In this case, the optimal market penetration rate could be between 40% and 60%. Also, a market penetration rate of 100% could be achieved by allowing the connected vehicles to use all the lanes. In this case, the conflict reduction could reach to 70% for a market penetration of 100% and could achieve 54% to 62% for a market penetration rate between 60% and 90%. Also, a market penetration rate lower than 10% was not recommended in the managed lane network. Then let's look at the second experiment in this project. The goal of this experiment is to evaluate the safety of the CV platoons by comparing the implementation of managed lane CV platoons and all lane CV platoons to the no connected vehicle scenario. Based on previous studies, platoon-based driving may significantly improve traffic safety and efficiency because a platoon has closer headways and lower speed variations than found in traditional traffic flow. In this study, we extend this effort to connected vehicle environment. The figure in the slide shows the studied area and the locations of the traffic detectors. A congested expressway in Orlando, Florida was selected as test bed for this study. The test bed was a 22-mile section of State Road 408 with 17 waving segments from West Colonial Drive, Orlando to Challenger Parkway, Orlando. This expressway is monitored by a microwave vehicle detection system, which indicates the base traffic characteristic of the selected roadway segment, and almost all ramps have an MVDS detectors. The simulated network was also well calibrated and validated based on field traffic data. In this study, 3 joining methods for connected vehicles, including rear, front, and cut-in join, were implemented to maintain the platoon. For the managed lane CV platoon scenario, platoons formed in the managed lane dedicated to connected vehicles, while in the all lanes CV platoon scenarios, platoon form in any lane of the roadway. The joining method of connected vehicles in managed lane CV and all lane CV scenarios are present in the left figures. The control algorithm architecture of managed lane is shown in the right figure. The all-lane CV platoon scenario is almost the same as the managed lane CV platoon scenario. Five surrogate safety measures are used to evaluate the safety of a managed lane CV platoon. The first surrogate safety measure is the TTC, which is the time to collision, which refers to the time that remains until a collision between the leading and the following vehicles will occur if the speed difference is maintained. The second surrogate safety measure is the TET, which refers to the total time spent under dangerous traffic conditions. The third surrogate safety measure is the TIT, refers to the entity of the TTC lower than the threshold. Also, the rear-end conflict risk is represented by TERCRI value. Sub-swipe conflict risk is represented by SSCR values. So in this table, we can find that the the CV managed lane scenario has the lowest risk for the mean values of the five surrogate indicators. So the scenarios with the managed lane CV platoons has the lowest conflict risk when compared to the all-lane CV platoon, while the scenario with the base conditions has the highest crash risk. One-way Anova were also conducted in this study. This slide shows the result of one-way Anova. The result indicates significant differences among these three scenarios. This indicates that managed lane CV platoons significantly outperformed all lane CV platoons. So based on the second experiment, we found connected vehicle managed lane has a lower conflict risk since the scenarios have smaller surrogate safety measure values. One-way Anova analysis confirmed the significant difference between managed lane and managed lane CV and all-lane CV. Finally, applying the CV managed lane in the transition period is worthwhile. That's all for my presentation. Thank you. I will be happy to take your questions.
Thanks, Yina.
The first question, I have a question regarding the scenario setup. In the figures, I can see some trucks in the leftmost lane in the managed lanes would be the most realistic and safer to prohibit trucks from using the leftmost lane. Okay. Yeah, so the first question most focused on the track in the most leftmost lane. So in the scenario, we have a certain percentage of the left of the track, and we don't have the we don't have the rules for the trucks to prohibit them from using the any lane, include the innermost lane. Yeah, this is something like we can test in the future experiment to consider if we need to prohibit those trucks in the innermost lane. So yeah, but the current the trucks can be in any of the lanes. And the second question is, are the vehicles in the CV platoon connected and automated? Yes. So if the vehicle in the CV platoon, we simulated them as a connected and automated vehicle. And what is your time headway setting in the CV platoon? So the car following model we used in the CV platoon based on the IDM model, which is calibrated for connected and autonomous vehicle. And so first the headway was calibrated based on the field data, and then we implemented the car following model based on the IDM model. So the car following behavior for the connected and autonomous vehicle will follow the IDM model. So any other questions?
I will mention right now we don't have any future webinars scheduled for the rest of 2019, so we will be off December at this point. However, if we do hear back from a project or two, we might throw one in before the holidays. If not, keep an eye out for future webinar announcements. We will get back to our regularly scheduled webinars on Tuesdays from 3 to 3:30 Eastern. So just keep an eye out for future announcements. I do see it looks like Lee might be typing another answer. Yina, I'm gonna mute myself and I'll let you take control back if you when this question comes in so you're able to answer it. Thank you. And it looks like it was more of a comment rather than a question. So that kind of gets to the one of the first questions that the trucks are not allowed to use the leftmost lanes on freeways and expressways in most cases. So that might be location dependent. Um, but in most cases, that's what it sounds like. So as you mentioned, Yina, that might be something to look into for future work or future studies. Controlling which lane specifically those trucks are in. Thank you, Lee. Well, it looks like that is. Oh, I do see some typing coming in. Um, That looks like that might be all the questions for today. Like I said, we will send this out here by the end of the week. So if you do have any follow-up questions, please feel free to reach out to that Safersim email address, and we can get you in touch with Yina. Or feel free to look her up on the University of Central Florida website, and I'm sure you can find her information there. Well, thank you everyone for joining. Thank you, Yina, for the presentation, and enjoy the rest of your day.